a cardinality, and that's where we're going to pick it up. So I'll, in a moment, I'll switch to the page, and we'll start reminding ourselves what is it that we were talking about. And essentially, what it means is to be able to say how big a set is, and we didn't get into actually defining cardinals. Instead, simply we talked about what it means for two sets to have the same cardinality. So that's where I'm going to pick it up. Let me go to the page. So let me just recall that. Let's put it over here. Recall that sets A and B have the same cardinality if there is a bijection F from A to B. And it's getting out of ink, so let me get another one. So we talked about this. We provided a few examples. So we said, for example, that the set of natural numbers has the same cardinality as the set of integers. Or we write A tilde B, or A is equivalent to B, to indicate that two sets have the same cardinality. So the natural numbers have the same cardinality as the integers. The natural numbers have the same cardinality as the one we define E, which is the even numbers, the even positive numbers. More precisely, the two n's, such that n ranges over the natural numbers. These two sets have the same cardinality. And so that's where we left it behind. So we now have a way of telling when two sets have the same cardinality. And then our next definition, which is definition 1.5.5 in our book, is the following. Definition 1.5.5. We say that a set A is countable. That's the new word we're learning. If the natural numbers and A have the same cardinality. And if we have an infinite set that is not countable, we call it uncountable. So countable means you can put it into one-to-one correspondence with the natural numbers. And if that cannot happen, then it is uncountable. Now, like I was telling you, most people, everyday people, when they think of infinite sets, they're actually thinking of countable infinite sets. Those are the types we have. And at this point, you may be thinking, is there even a difference, right? I mean, are there really infinite sets that are uncountable? And we'll talk more about that today. And it turns out that there are, right? And in a certain sense, the countable sets are the smaller possible infinite sets. I mean, we're not going to do this in this class, but if you were to take a set theory class where you looked at infinite sets, you would define cardinals, and the cardinal corresponding to the natural numbers, the cardinality of the natural numbers, if you want to, is named as Aleph 0, right? So it's a a Hebrew letter, Aleph 0. This is Aleph 0, Aleph 0. This is the cardinality of the natural numbers, right? And we won't talk about it in these terms in this class, but just a little bit of general knowledge for you. And then it turns out that there are, like I mentioned last time, there are infinite sets that are bigger than others. So there is such a thing as Aleph 1 and Aleph 2 and Aleph 3, etc. And you wouldn't even believe how big those infinite sets can get. Okay, so at this point, I wanted to, so we already looked at some things that are intuitively weird about infinite sets, right? For instance, last class, we talked about how it's possible to have you know, two sets where one is inside the other, right? The natural numbers are a subset of the integers, and yet they have the same cardinality. They are as big. So there are as many natural numbers as there are integers, even though this is a subset of that, right? Even though you would consider this a larger set, right, in the sense that it contains the natural numbers, as a matter of fact, they have the same size. And that's something that does not happen with finite sets, right? If you have a finite set and it contains another one, the other one is for sure smaller in size. And this, you can see, it doesn't happen here. So at this point in the class, before we move up to the next theorem, which is actually quite nice, I usually like to talk to you about the following mental experiment of the types of things that can happen when you have infinite sets. Okay, so consider the following. Consider, if you can, imagine that you guys are the owners of an infinite hotel. More precisely, a countable hotel. So we have a countable hotel. So what I mean by this is that you have a lot of rooms, infinitely many rooms, and they are numbered. There's room 1, room 2, room 3. They are numbered using the natural numbers, hence countable, right? So the function that numbers the hotel rooms is the bijection we're talking about, between the number of rooms, between the rooms in the hotel and the natural numbers. So there's a room 1, and a room 2, and a room 3, etc., right? And then consider the following situation. See, this is what's happening. The hotel at this point is actually packed, is at full capacity. Every single one of your rooms is occupied. And you get a new customer, a new guest checking in. And then your task is to come up with a way to actually assign a room to the guest, of course, without taking any of the current occupying guests away, okay? So what do we do? How can we make space for this new guest to the hotel? What do you think?
How could it be full capacity though if it goes on and on?
Well, every one of the rooms is occupied, right? I mean, of course, there's infinite number of people in this mental experiment. I know that's impossible, right? There is no infinite number of people, but that's why we call it an infinite, a mental experiment. So Leon said, add 1 to the last room number. Well, there is no last room number, right? It is the natural numbers. See, it's like when you played this game when you were children of saying bigger and bigger numbers. You can never win that game, right? If you say 44, I say 45, or any number bigger than 44, and so on, right? It doesn't matter how big a number you choose, there's always a number that is larger than that.
One way to do it would be to have every guest move to the next room in the line, so then the first room opens up.
Exactly. Yeah, that works. So you can go and give the following announcement. Dear guests, please, if you are so kind, please relocate to the next room. So if you were in room 74, good, go to room 75. If you were in room 1,847,343, you go to room 1,847,344, right? And so on. So everyone moves to the next room. So the guest that was in room 1 goes to room 2, and the guest in room 2 goes to room 3, and the guest in room 3 goes to room 4, and this continues, right? So the guest in room 124 goes to room 125, and so on. Okay. All right, and then room 1 is empty, correct? So that's what we can do now. So room 1 is empty, and we assign that room 1 to our new guest. Okay, so yes, this works. Okay, so that's the first level of difficulty in this mental experiment. So that's how to deal with one new guest. One new guest. Okay, now here's the thing now. All right, so now here's a newer situation. This time around, we are getting a boss. So, okay, babe, before we do that, if instead of one new guest, we had, say, 10 new guests come and each one of them want their own room, you already know how to fix this, right? You can either repeat this process 10 times, or if you don't want to do that, you can simply now tell everyone to move to the room 10 units more, right? So you have room 1 person go to room 11, room 2 to room 12, room 3 to room 13, etc. Everyone moves 10 to the room that is 10 units extra. And in that way, you leave rooms 1 through 10 free, available for the 10 guests, right? So that one is not that bad. That's almost the same thing. So here's a new one. So this time we get a boss. We get an infinite boss. Infinite boss. So countable. So what I mean by this is a boss that has infinitely many people inside, right? It has a countable number of people inside that boss. And each one of them has their own room. They don't want to share. So we have to house these people, this infinite number of people, but our hotel is already packed. It's already occupied at its capacity. How do we deal with this? How do we do that now?
Can you explain like how it's countable even though it's infinite? Does that mean just like you're just gonna keep counting?
Countable means is infinite and it's in one-to-one relationship with the natural numbers, right? Countable means I can do it like this. I can say the first, the second, the third, the fourth, etc. Does that make sense? Now, probably this will you will understand this better when later on I show you a set that is uncountable, right? Because right now for you, countable and infinite probably mean the same thing. So don't worry too much at this point if you don't get it. But countable means one-to-one correspondence with the natural numbers. All right, so back to our mental exercise. How do we do this?
Maybe we could take the person in room R sub n to room R sub 2n.
Yeah, that can work, right? So that's a good idea. Very nice. So here's the thing. Look at this. So this time we ask everyone, like, who was that? Was that David?
Yeah.
Yeah, like David just said. So you ask every person to move to the room that is double, right? So if you were in room 1, now you go to room 2. If you were in room 2, you go to room 4. If you were in room 3, you go to room 6. And then if you were in room 4, you go to room 8. I mean, there's a problem. I mean, I don't know how far apart these rooms are. Maybe people are going to need to walk a lot. But let's not worry ourselves about that, okay? So everyone moves to a room that is twice as big. And then that's awesome because now all these other ones are empty, right? Room 1 is empty, room 3 is empty, room 5 is empty, room 7 is empty, room 9 is empty, right? Because these are odd numbers. They won't get anyone, right? You're only going to numbers that are double something else. So these guys are empty. These are empty. All of these. And those are the ones where we can tell the people in our infinite boss to occupy, right? So then you go like this. Okay, fantastic. So now the first person in the boss, you go to room 1. The second person in the boss, you go to the second odd number. That's 3. The third person in the infinite boss, you go to the third odd number. That's 5, and so on, right? So in general, the nth person in the boss, nth person in boss, will go to room 2n plus 1, right? Like this, 2n plus 1. That's the room you're going to occupy. Is that clear?
Does that mean that, would you be able to do it with any multiplication, like 3n or like 3n? Would it be the same thing? like the same idea? Every 3, they move every 3 rooms.
If you multiply by 3, it works, but now you're gonna get, yeah, so you're actually doing the next problem. You would multiply by 3 if instead of having 1 infinite boss, you get 2 infinite bosses, right? Do you see that? See, if you have 2 infinite bosses, then you ask every person to move to triple their room, right? And in that way, you're gonna leave 2 infinite sets free for the 2 infinite bosses. Does that make sense?
Professor, I have a question.
Yeah, go ahead.
If we're doing 2n plus 1, isn't that first room going to be empty? How come we don't do 2n minus 1?
I don't know what you're talking about.
Because you said that.
Didn't I say 2n minus 1? I'm just joking. You're right. You are right. It should be 2n minus 1. Otherwise, I leave. Well, I mean, it's still correct. I mean, I still found a way to give everyone a room if I use 2n plus 1, but then room number 1 would be empty. So you are right. It's probably better to use 2n minus 1.
Yeah, because you don't want to lose the income for that one room out of the infinite number of rooms.
There you go. Very good. You know, infinite number of money. Okay. So yeah. So to your question, if you multiply by 3, you could now do it with three infinite bosses, right? I mean 2 infinite bosses. So 2 infinite bosses. So let me call them B and C. So you have B1, B2, B3, infinite, and then C1, C2, C3. So these are the people in boss 1, and these are the people in boss 2, right? And then here are the rooms. Room 1, room 2, room 3, room 4, and what you're gonna do is you are gonna ask everyone to go to triple the room. So this guy will go to room 3, this guy will go to room 6, and then this guy go to room 9, right? Everyone gets their own room. But now look, now you have all of these ones free. So you have room 1, room 4, and room 7, and room 10 free, but also, and I'm using a different color, I hope you can appreciate it, we have room 2 and room 5 and room 8 and room 12 free, right? So that's what, in these free rooms, that's where I'm gonna house the people in these 2 infinite bosses. So I'm gonna send these guys to the B's. So the red ones, I'm gonna send, I'm gonna use the B's. And on the green ones, I'm gonna use the C's. Now, if you're thinking that I'm just losing my time showing you these little problems, these are actually hints for many of the problems in your homework, where you're asked to show, for example, that if you have 2 infinite sets, then their union is also infinite. Or if you have 3 infinite sets, then their union is infinite. This is kind of like the hint of how to do it, right? So here, what we're doing is the nth person in boss B, we're sending it to room 3n minus 2, and the nth person in boss C, we're sending it to room 3n minus 1.
And that's because it's more convenient than having like everybody having to move each time, right?
Yes. Yeah, okay, so you're saying yes. So this is if we wanted to do it once, because you could do the previous process just twice, right? I guess that's what you're saying. We could repeat the same process that we did before twice. Yeah. Once for the first boss. Yes, absolutely. That will work too. Now, the one that I'm not gonna do, I'm just gonna leave it for you, right? To think about how you would do it. The next level of difficulty here would be if you now get not 1 boss, not 2 bosses, not 3 of them, you get infinitely many bosses, all right? So you get a lot of bosses, infinitely many of them, and each one of them has infinitely many people. And now your goal is the same. So you need to, your hotel is already full. You need to be able to house everyone. Okay, that I won't tell you how to do it. It's good to leave something for you to think. But it's just these crazy things that can happen with infinite sets, okay? It's really something else. All right, so let's bring it back now to our theorem. So this theorem 1.5.6 says the following. It says, has two parts. Part one, the set Q, the rational numbers, is countable. All right, so this tells you that there are as many rational numbers as there are integers, positive integers. They're the same cardinality. And here is the one that is going to be, I hope, surprising to those that don't know. The set of real numbers is uncountable. Okay, so in that sense, the real numbers are infinite, but they are larger than the natural numbers. It's a bigger infinite, okay? It's an infinite set, obviously. It is obviously an infinite set, but it's not countable. So you cannot do a one-to-one correspondence with the natural numbers. When you try to do it, you always have extra real numbers. You have always leftover real numbers, which means the real numbers are more. Right? The cardinality of the real numbers is larger than the cardinality of the natural numbers, believe it or not.
Because of the irrationals.
Yes, that as a consequence of this, you could prove that the irrationals are uncountable, right? So the rationals are countable, but the irrationals are uncountable.
Wait, can you explain uncountable with like in an example? Or?
Well, this is my example, right?
It's like I kind of get it, but I don't see it yet.
Well, you don't get it, but it's because I haven't explained why. Yeah? So let me show you why. So let's prove this theorem and say, why is it uncountable, right? Why can't we make a list of real numbers, right? Maybe this is the first real number, the second, the third, the fourth. We number them somehow. Why can't we do that is the question. And yet we can do it for Q, right? You can count the rational numbers. Now, there are several ways of counting the rational numbers, so we're going to start with the proof of one. There are several ways. In fact, in your book, in your homework, they suggest one way of doing it in exercise 1.5.3. But we're going to do it the way it's in our book. I actually like the proof in our book. Okay, so here's what we're gonna do. We're gonna divide the rational numbers. So we're gonna do the proof of one. So we're going to partition. We will partition Q into countably many finite sets. And then I'll tell you how this helps to create the bijection. All right. So here are the finite sets. The first, they're going to be called A's. The first one, A1, is the set that only has 0. All right? It's not the empty set. It's the set that has the number 0. Okay, that's the first one. And that's the only one that's a little bit special. All the others will be defined like this. You will have all the rational numbers P over Q, where this is in simplified form. So we can say that by saying that the greatest common divisor of P and Q is 1. And P plus Q is either N or negative N. That's our definition, okay? Now let's try to make sense of this definition, starting with the easiest of them all. So what would be A sub 2? Okay, so we need numbers that when you add them together, the P and the Q, you get 2 or negative 2. Well, these numbers have to be integers, right? So there's only two choices. Either has to be 1 divided by 1, right? Or negative 1 divided by, I'm not doing this right. Hold on a sec. I didn't write it correctly. So this is the plus or minus. You include here either the positives or the negatives. So if I had 1 over 1, I should also have negative 1 over 1, right? Because 1 and 1 add up to 2. And that's it. I mean, you can have other possibilities. So the plus or minus does not go there. It goes, let me fix it. My math, I copied wrong. It should be n here. And we do have a plus or minus here. Okay, so the only chance here of P and Q is 1 and 1. Because if you pick any other numbers, they are going to add up to something bigger than 1, right? 2 and 1 or 1 and 2, that would be adding up to 3. Okay, so these P and Q are supposed to be natural numbers, positive integers. So A2 is just 1 and negative 1. Let's check the one, a few more. What about A3? What are the elements of A3? So now the numbers add up to 3, right? The numerator and the denominator add up to 3. So we can have 2 over 1, or we can have 1 over 2, and the negatives of these, right? Negative 1/2 and negative 2. Yes? Let's try a few more. How about A4? Now the numbers should add up to 4. So we start with 3 over 1.
But the negative, isn't it like negative 1 plus 1? That would give you 1 negative.
Yeah, that was my mistake when I wrote it initially. But see, so that's why we have plus and minus here. So you're supposed to have two numbers that add up to 2, and those two numbers are 1 and 1. Okay? And then you are allowed to put a plus or a minus, whichever way you want. Is that clear?
Oh, okay.
So over here, maybe you're thinking, how about 2 over 2? I mean, they add up to 4, right? But the problem with this is that the GCD is not 1. This is a fraction that is not reduced. So this one, 2 and 2 should not be there. So that shouldn't be included. So we go 3, 1, then the next one, 1/3, that works. And then the negatives of those, negative 1/3 and negative 3. All right, and I'll do one more. How about A5? A5 is actually a little bit bigger. For A5, we have 4 over 1, we have 3 over 2, 2 over 3, and 1 over 4. And the negatives of this. So negative 1/4, negative 2/3, negative 3/2, and negative 4 over 1. All right, now here's the thing. This is the part that I want to convince you that this is thorough. Think of any rational number, no matter which rational number, and I can show you that that rational number is in one of these sets, right? So let's try a weird rational number. How about 17 over 91? In which A will this guy be, right? And I claim that this guy belongs to A 108. Do you believe that? Well, you should, because this is in reduced form. 91 is not a multiple of 17. So this is already reduced. And what is the sum of 17 plus 91?
108.
Yeah, 108. So that's why this guy belongs in there, right? So every rational number that you can think of, no matter how, so if it's already reduced, so in general, P over Q, if it's reduced with GCD of P and Q equals 1, in general, P over Q belongs to A, P plus Q, right? Because the sum of these two guys will be P and Q if it is positive. And if it is negative, well, then as well. I mean, you just make sure that you only add the positive numbers, right? So every rational number is in one of these A's. Okay, is that clear? So then the only thing we need to do is to write down the function. Now, we're not going to write it. I just want to show you that it can be done. So if you wanted to number the rational numbers, how could you number them? Well, here's one way we can number them. We can go like this. This is going to be the first rational number, the first element of A1. Then this is going to be the second, and this is going to be the third. And then this is going to be the fourth, and this will be the fifth, and the sixth, and the seventh. And then we go to the next A, and that we go 8, 9, 10, 11. And then we go A5, and this will be the 12th, the 13th, the 14th, the 15th, the 16th, the 17th, and the 18th, and the 19th. And then we go to A6 to do the 20th, the 21, the 22nd, etc. Okay? And do you see that I can number everyone like this? And I will cover everybody because everybody belongs to one of these A's. And I wouldn't repeat anyone because every number is in only one of these A's. So there will be no repetitions. So I will cover all the rational numbers. It will be onto, and it would be one-to-one because no rational number will be repeated in this list. So that's the part. I mean, it would be really awkward and complicated to actually tell you the precise function. If you want a formula for the function, it will be complicated. We could do it, but it will take the entire class for us to write it down with precision, and it's not worth it. Okay? So, but it should be clear that we can number all rational numbers by proceeding to number each element in AI recursively. So that means we start in A1, then A2, then A3, then A4. So in this way, let me just provide a bit more explanation of why we have the properties that we want. So because every rational number belongs to exactly one AI, this enumeration would be onto and one-to-one. Right? So that is the way we can find out transform a function from the natural numbers to the set of rational numbers. So if you ask me what is, so I'm not, as I said, I didn't tell it to you explicitly, but if I want to know, okay, what would be f of 5? Well, I go here in my list and I go, okay, which one is the fifth one? 1, 2, 3, 4, 5 is 1/2. So f of 5 is 1/2. All right. If I want to know what is f of 11, well, I go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 is -3/2. All right. But I'm not showing you a specific formula because that would be really, really complicated. But I hope you're convinced that when we do it, if we keep numbering like this, then every rational number will appear in this list at some point, and we will never have repetitions. Those are the important parts. Okay? All right. So now for the second part, let's try to do the same thing for the real numbers. How come for the real numbers it doesn't work? That's the question, right? So for part 2, let's suppose we can do it. So suppose we can find f from the natural numbers to the real numbers, which is a bijection. So it's onto and it is one-to-one. Suppose we could do it. So in other words, suppose we can count the rational numbers, i.e., suppose we can count the real numbers, right? Count means we can, precisely this, there is a function from the natural numbers to the real numbers, which is one-to-one. Okay, all right, so this is what we're gonna do. We're going to, just for simplicity, so this is f, so for every, so f of 1 is the first real number, and f of 2 would be the second real number, and f of 3 would be the third, and so on. And we don't know which ones are there. We just know there is some way of doing it, okay? So let's just give it a name. Let xj be f of j. So this is the jth real number, right? The jth real number, we're calling it x sub j, okay? And now this is what we're gonna be doing. So let me do a little bit of a picture here. So imagine we have the real line, and somewhere over here is x1, right? I don't know where, because the function picked some real number to be the first one. I don't know which one the function picked, but there is one that is the first. So here's what we're gonna be doing now. So pick an interval, a closed interval, that does not contain x1. So let I1 be an interval, closed interval. Okay, more particular here, it's important that it's closed. Let I1 be a closed interval not containing x1. All right, so which one, you may ask? Well, pick whichever one you want. So where do you want it? Do you want it on the left side of x1 or on the right side of x1? I don't care. Either one will work. So let's pick this one, for example. This will be I1. This interval from here to here. And obviously x1 is outside, right? So we're good. Okay, and then we're gonna do the same thing. So now pick, now somewhere over here is x2. So we're gonna continue the same way. We're gonna say that I2 will be a closed interval not containing x2, but inside I1. And this is also easy to do, right? So here's how you can do it. See, there's two possibilities. One possibility is that your x2 is somewhere over here, outside of I1. And if that's the case, put I1, put I2 wherever you want. Anywhere inside I1, doesn't matter. So that's the easy case. The bad case, the difficult case, is if x2 is inside I1. So what if x2 is inside I1? Well, if that happens, doesn't matter. You still have space, right? You have space right here on the left or on the right. So just pick one side. It really doesn't matter which side. I'm gonna put it on the right. So I'm gonna pick this one as I2, right? So this is I2. And you can tell that I2 doesn't have x2. All right? Is that clear? Good. So now we're gonna keep doing this, right? So we did the first interval and the second interval, so let's do the third. So in general, let In be a closed interval inside In minus 1. By inside, I mean a subset, such that Xn does not belong to In. Does not. So it avoids In, right? So if I wanted to continue in my picture, the bad case would be that X3 is maybe in here. So then I need to pick an interval where X3 is not there. So maybe I'll pick this one over here. That would be I3. Okay. All right. So, and we continue like that. We can do this for every n. So we do I1, I2, I3, I4, I5, I6, etc. All of them. All right. Okay. And then why are we doing this? You may be wondering. Well, if this hasn't ring a bell yet, it should. I mean, we want to use the nested interval property. Remember that one? We proved that as a consequence of the axiom of completeness. We said that if we have a sequence of closed intervals, then their intersection is non-empty. So let's write that down. That's going to be important. So notice that we have I1 contains I2, which contains I3, which contains I4, etc. So this is a sequence of nested intervals. So by the nested interval property, we have that their intersection, if we intersect all of them, is non-empty, right? That's what the nested interval property says. It says that the intersection of all of these guys is non-empty, right? So there must be some point that that belongs to the intersection, right? And I'm going to show you how we're going to get a contradiction, because imagine that somebody belongs to this intersection. Let's call it alpha. Suppose that alpha belongs to the intersection of all of them, right? Suppose that happens. Well, we're going to get a contradiction, and I'll tell you why. Because this alpha is a real number, right? And because it's a real number, and we started with a function f, where is it? Right here. See, f is a bijection. A bijection means that any real number receives an arrow, right? So this guy must receive an arrow from from someone, right? So because f is onto, there is some natural number m such that f of m, which by the way we denoted it as xm, equals alpha, right? So the function f is onto. That means somebody must arrow alpha, and this is the somebody. We're calling it m. So f of m goes to alpha. All right? Okay, but then when we go to our definition of our intervals, what happens when we get to the mth interval, right? So I'm gonna write that here. However, by definition, by definition, the interval Im does not have xm inside. Remember that that's how we constructed these intervals. To construct the first one, we excluded x1. To construct the second one, we excluded x2, and so on. So when it comes the time to construct the mth one, we're gonna exclude xm, right? So that's a contradiction. Why is this a contradiction? Because xm equals alpha, right? So alpha is not inside Im. This is a contradiction because it says that alpha, which is xm, is not inside Im. But over here, this one over here, actually this one, says that alpha is in all of them, right? This one says that alpha belongs to all of them. And this one says it doesn't belong to Im. So these two are contradictory of each other, right? How you cannot simultaneously belong to all of them and not belong to Im.
So it's kind of like what you were drawing, where like the Im would, like xm would be outside of Im.
Yes, exactly. Xm would be outside of Im. So then who can be in the intersection, right? Because by construction, the way we constructed our intervals, we're always excluding someone, right? The way we constructed our intervals, we're excluding one, and we're excluding another, and excluding another, and excluding another. We're excluding someone at every stage. So it's impossible for the intersection to have anybody. See, the intersection should be empty. And however, the nested interval property says that the intersection cannot be empty. So something's wrong. And so where is it? I mean, we got something wrong here. What's the only thing we assumed? The only thing we assumed is right here at the top. That we can find this function. That's what's wrong to begin with. So the only logical conclusion is that this function does not exist, right? This function f cannot happen. In fact, if you looked a little bit more close into our proof, you'll notice that I didn't use bijection. See, the only property that I used was onto. We used it right here, because f is onto, this happens. So we proved something stronger. We proved that there is no surjective function that makes this happen, right? There are no onto functions from the natural numbers to the real numbers. We didn't even use the one-to-one thing. We only use the onto part, okay? So this is the end of the proof. Yes, very nice proof. In fact, when people first discovered this, it was a little bit crazy. People at the Cantor, which was the first one that established that the real numbers had a larger cardinality, kind of went crazy because of this discovery. I mean, it contradicted the notion that everyone had before, that all infinite sets were the same size. And that this really came as a shock to the mathematical community at that time. All right, so this is the end of this proof. We have something, a couple of other theorems that I'm gonna announce but not prove. Many of them you need to find ways to proving them from your homework exercises, right? But it's important that you know them. This is the first, theorem 1.5.7 in the book. It says the following: if A is a subset of B and B is countable, then A is finite or countable. In other words, if you have something countable, then every subset is also countable or finite, right? Finite means that it's even smaller. That's one of them. And the other one is the one that relates to the hotels, to the infinite hotel we were talking about before, is this one over here. It says the following: if you have a bunch of countable sets, think of this as the bosses, are each countable, then the union is countable. That's part one. And part two of this theorem is the second part of the hotel analogy, is where you get infinitely many hotels. If an is countable for each n, then the union from 1 to infinity is also countable. Informally, we say here that the countable union of countable sets is countable, right? So if you put together countably many countable sets, you get something countable. So there's no way you can surpass countable by combining countable things. That's the essence of this theorem over here. Okay, so this is going to be the end of chapter 1. You'll notice in the book there's another section, 1.6. I mentioned this at the beginning of the semester. Generally, our book, the last section of every chapter is meant to have a topic that is a bit more advanced, in which you sort of discover the results on your own by doing exercises. It's fantastic. I wish we would have the time to go over this. We actually are going to do one in chapter 5, I believe. It's one that I cannot let pass. It relates to the, if you look at your Canvas page, I put a graph that it is a graph that represents the icon of our class, and that's about 5.4. So 5.4, we will actually do it, but that's the only one where the only time we're going to cover the last section of a chapter. So that doesn't mean it's not not relevant or not interesting. If you have the time, by all means, take a look at it, read through it. It's great stuff, but we simply don't have the time to cover it in detail here in class. So instead, we're gonna move on to chapter 2, right?
Professor,
Yes.
are we going to have another homework assignment assigned today?
Not today. We don't have a homework assignment or a quiz for today. Okay. We'll have something next class.
Okay.
So this is chapter 2, and it's called Sequences and Series. So a little note here. If you remember the way in which we did things in calculus, if it wasn't not too long ago that you took a calculus class, that this is not the order in which things are done, right? So you actually first learn limits, and then derivatives, and then integrals, and then you do sequences and series in 150B. Okay, so the order here will be slightly different. The advantage is that you guys should already know about these things. All right, so you already took the calculus sequence. You know already these concepts. That's why we had the diagnostic test, as a way for me to show you that this part of the material you're supposed to know already. Okay, in this class, we're learning why rather than what, right? You're already supposed to know what, and here we're learning why. So same as in chapter 1, the first section does not have any exercises, and it's meant to be an introduction, a way to motivate why we are studying these types of things, and why is it that we need to be really, really careful when we look at infinite things. Okay, so that's what I'm going to do. I'm going to talk a little bit of what is left of today's class about that section 2.1 as a way to motivate what is it that we're going to be doing here. And the first one, the first way to motivate this is for you to remember that when we take a series, we need to be careful in the way we define how things are added, right? So maybe you remember this series from your calculus days. It's called the alternating harmonic series. It's -1 to the n plus 1 over n, from 1 to infinity. Is this series over here is 1 minus 1/2 plus 1/3 minus 1/4 plus 1/5 minus 1/6, etc. And you should remember it that it converges. So when you do the partial sums, in the end you get a number, right? Maybe some of you even know what that number is. Not that it's relevant here, but this is actually convergent, and it's called the alternating harmonic series. And it is convergent. Convergent. Okay. So I don't want to tell you what the answer to this is, but it's some number. So it really is some number. So S equals this: 1 minus 1/2 plus 1/3 minus 1/4 plus 1/5 minus 1/6. I'm going to write more terms. So I'm going to do something with it. Okay, these are enough. All right, now here's what I'm telling you where you need to be careful. Let's do the following. Let's multiply this guy by 1/2. So let's do 1/2 of S. Okay, and I'm gonna space it in a different way so that you can appreciate what is it that I'm doing here. So I'm gonna multiply this guy by 1/2. So 1/2 times 1, that's 1/2. And I'm going to place that 1/2 right, where is it that I want it? Right here. So 1/2 times 1 is 1/2. Then 1/2 times -1/2, that's -1/4, right? And I'm going to put it here. And then 1/2 times 1/3, that's 1/6. And I'm going to put it here. And then 1/2 times negative 1/4 is negative 1/8. I'm going to put it here. And then 1/2 times 1/5, that's 1/10, and I'm going to put it here. Positive 1/10, and so on, right? So I'm just multiplying this one by 1/2, but I'm placing them like this because of the following. This is what I'm going to do. Now I'm going to add these two together, right? Now, if you believe that things are fine, that you're, I mean, if this one is some number and I multiply it by 1/2, I should get, the answer should be 1/2 of that answer, right? Should be 1/2 of S. So when I add these two things together, let's see what we get. We should get 3/2 of S, right? So it's a whole plus 1/2, that's 3/2. And now look at what we're gonna get here. This guy will be 1. Now I'm adding like this, vertically, okay? So what is negative 1/2 plus 1/2? 0, right? So nothing there. So we skip that one. And then I have 1/3. And then negative 1/4 and negative 1/4. What is that?
Negative 1/2.
Yeah, negative 1/2. Good. Then this 1/5 just comes like this. Then this 2 is a negative 1/6, and 1/6 goes away. Then I got a 1/7. Then a negative 1/4, right? Then 1/9. Then this one goes away. Then positive 1/11, etc. Right? Okay. Now looking here, and you'll notice that this one over here, the one we just did, looks a lot like the first. In fact, you pretty much have the same numbers. Look, here's the 1, here's the 1, here's the negative 1/2. It's just in a different spot, right? So negative 1/2 now is over here, before it was before, but that doesn't matter. If you flip these two, you'll get it, right? So negative 1/2 is there, 1/3 is there, negative 1/4 is over here. You see it? 1/5 is there. 1/6, we don't see it yet, but it will appear when we go all the way over here to negative 1/12. Negative 1/12. This is going to have over here also negative 1/12. And when we add these two, it's going to be negative 1/6. So negative 1/6 is there too. It only happens later, but it's there. And then 1/7, and then 1/8 will happen even later, and then 1/9, etc. My point that I'm trying to make is that the terms here are the same as the original one, only in a different order, right? So look at what we just did here, right? If, probably you believe that you probably learned this in elementary school, that if you do 2 plus 3, that's the same as 3 plus 2, right? If you change the order, it doesn't matter. You get the same answer. Yeah? Well, look here. If we add these numbers in this way, 1, negative 1/2, plus 1/3, negative 4, plus 1/5, negative 6, we get some number S. But if we add them in this way, 1, 1/3, negative 1/2, 1/5, 1/7, negative 1/4. So the order here, what we're doing is 2 odd ones, then the negative even. 2 odd ones, then the negative even. 2 odd ones, then the negative even. Whereas over here, we were doing odd, even, odd, even, odd, even, alternating signs, right? Here we're doing them in a different order. And just by changing the order, the sum is different, right? How can this be? So both the first and the third series have the same terms, only a different order. Yet the sums are different. What? How can that be, right? Well, we're gonna learn. We're gonna learn why this happens, and actually why we need to be really, really careful in the way we define what it means for these infinite sums to make sense. Because the properties that we are used to having for finite sums, like 2 plus 3 equals 3 plus 2, maybe they don't hold anymore. Like here, it doesn't work anymore, right? Here's another example, probably an easier one. See, maybe you've seen this one. What is this one? -1 plus 1, -1 plus 1, -1 plus 1, -1 plus 1, -1 plus 1. What is the answer to this one? Right? If this is S, what is S? And here's the thing, right? If you put the first two together, and then the next two, and then the next two, and then the next two, what do you get?
0.
Yeah, I mean, this is 0, and this is 0, and this is 0, and so we're adding a bunch of zeros, so the answer should be 0, right? But if we do the same trick, but we leave the first one by itself, look what happens. These that I put in parentheses are still zeros. So this is still 0, and 0, and 0. But we have the first one that is -1. So the answer is -1. What? Which one is it? Is it 0 or is it -1? It cannot be both, right? If the answer exists, it should be only one of them. And in this case, what's happening? How could it be two different ones, right? So again, I don't intend to tell you the answers to these questions yet. I'm just showing you that we need to be really, really careful when we consider infinitely many things. All right. Here's another one. I like this one too. So consider now this infinite array of numbers, right? So here's one. It's -1, 1/2, 1/4, 1/8, 1/16, 1/32, etc. And then on the bottom, I'm gonna do this. Just put a 0 and then move it 1 unit to the right. And now 2 zeros and move it 1 unit to the right. And then 3 zeros and move it 1 unit to the right. And 4 zeros. And notice, I mean, this should be, so it continues, right? So it's an infinite thing. So even though I'm not writing the numbers here, these numbers should continue, okay? So over the next one over here is 1/64, and then 1/32, 1/16, 1/8, etc. Right? We have this infinite array of numbers. So over here is 1/64, 1/32, 1/16. If I were to write the next term, 1/2, and then this one would be -1, and these guys would be zeros, and so on. So I can keep writing it. All right. Now imagine that I want to add all of these numbers, right? I want to add up all of the numbers in this array when I'm done. Okay. Now I'm gonna show you the crazy things that can happen if you do this different ways. For example, let's add by rows, right? What is the sum of each row? What would be the sum of each row? If we add up these numbers, what do we get? Well, maybe you remember, what is 1/2 plus 1/4 plus 1/8 plus 1/16 plus 1/32 plus 1/64? What is the sum of that? Is this one. 1/2 to the 1/2 to the n from 1 to infinity. What is the answer to that one? It's a geometric sum, right? I like to think of it with a picture. So here's 0 and here's 1. So we first go 1/2 from here to here. Then we add 1/4, which is half the remaining distance, right? So this distance from here to here is 1/4. And then we add half of the remaining distance. That's the 1/8. And then half of the remaining distance, and then half and half and half. What is the sum of all of it?
1.
Yeah, it is 1. That's a geometric sum, and it is 1. So all of these numbers add up to 1, but then you put the -1, what do you get?
0.
Yeah, so this row adds up to 0. Second row is the same thing, right? Because you still have 1/2, 1/4, 1/8, 1/16, 1/32, all of those. All of these guys add up to 1, -1, that's a 0, and then another 0. Fine, the sum is 0. And then the same one for this one, right? It's a half, a fourth, an eighth, 16, etc. All of these add up to 1. With this -1 is a 0, 0, and 0. So this is 0. So all the rows have a sum of 0. So if you add up all the rows, what you're going to get is 0. Is that clear? Yeah? Now let's go by columns. Now let's add up by columns. So over here now, let me put the sum of the column. Right? So what about this first column? That's easy because there's only a -1 and a bunch of zeros. So the sum is -1. Right? -1. Then for the next one, I have 1 and -1/2 and -1. So the answer is -1/2. Right? The one after that, I have 1/4 and 1/2. That's 3/4. But then subtract -1, so that's -1/4. -1/4. For the next one, I have 1/8, 1/4, 1/2, and -1. So these three together add up to 7/8. And when you subtract 1, you get -1/8. Okay? And this pattern continues. So this is going to be -1/16, -1/32, -1/64, etc. That's what the sum of the columns are. So then if I add up the columns, if I add all of these numbers together, from here to here, I'm going to get -1. And this other -1, it's going to be -2. So the total sum would be -2. So the sum of all the column sums is -2. Okay, right? Are you guys going crazy? How could this be, right? I mean, these are not even difficult numbers. How come we're getting different answers? If we add it up by rows, every row is 0. So then you were thinking, oh, then the sum of these numbers is 0. But if we go by columns, this guy is -1, this is -1/2, -4, -8, etc. And when we add them all together, we get -2. So which is it? Is it 0 or is it -2? What's the truth there, right? What's happening here? Yeah, obviously it cannot be both things. It cannot be 0 and -2. So one of these is not right. And that's exactly what we want to quantify and make really, really precise. So like I said, all of these that I just showed you is a way to motivate you to think about, wow, this is crazy. I never thought this could happen. What's going on? I gotta learn. I have to know, how do you define these things, these sums, right? All my examples were about infinite sums or series, right? So how are series correctly defined so that none of this nonsense happens? And that's what we're gonna be eventually learning. But before that, we're gonna start with sequences. So this will be the last thing we're gonna do today. I want to define to you what a sequence is. And so before we can talk about series, we need to talk about sequences. So here is our first definition of chapter 2, definition 2.2.1. What is a sequence? And it will sound familiar because it's something we've seen before. So a sequence is a function f from the natural numbers to the real numbers. That's what it is. That's what a sequence is, right? It's like a numbering of some real numbers. Right? On the previous theorem, we saw that it's impossible to for this to be onto, right? If you try to make it onto, you cannot. There are always leftover real numbers. But that's fine. Maybe you don't want all of them. You just want a few of them. And we call f of n is the nth member of the list. So here are a few examples. So we can define a sequence like this. You can name the elements. So there's different ways of writing it. So we can write like this: 1, 1/2, 1/3, 1/4, 1/5. Right? That's one way of writing it. That's the same as writing it this way. This is 1 over n, from 1 to infinity. Right? And the book uses parentheses. This is different from book to book, okay? In our book, we use just regular parentheses to denote the sequence. And what is a function? I mean, I talked about a function here, and there is no function here. Well, there is no function because it's implicit what the function is. This is the first element. This is the second. This is the third. This is the fourth. This is the fifth. So when we write it like this is really this. This is f of 1, f of 2, f of 3. When you list the elements, you're supposed to list them in order according to the function. So here, the function is actually, so here, f of n is actually 1 over n, right? So the first element in my sequence is 1. When I want to know what is the fifth element, I plug 5 here. F of 5 is 1 over 5. 1, 2, 3, 4, 5, that's 1 over 5. Yeah, that's correct. Okay, so these are 4 different ways of writing the same sequence. Important, if you write it like the first, it has to be clear what is the pattern here, right? Because I have to know that the one that follows is 1 over 6. And if the pattern is not clear, then you should avoid this way of writing things down. So here's a few others. So for example, it could be this one, 1 plus n over n, from 1 to infinity, right? So this is, the first one would be when n is 1. So this would be 2. And then after that is when n is 2. So that's 3/2. And then 4/3. And then 5/4. And 6/5. And 7/6, etc. Right? In general, the formula is n plus 1 over n. So here the function is 1 plus n over n. Okay? A couple more examples. You can, like I said, you can give it a name like this. This is my sequence, an, from 1 to infinity. And I just then tell you what an is, where an is 2 to the n. That's perfectly fine, right? You can, again, list some of the elements of this sequence if you wanted to. So it starts with n is 1. So the first one is 2, then 2 squared, and then 2 cubed, and then 2 to the 4th, 2 to the 5th, etc. And one last example. You can also define them in a recursive way. So you can say we have a sequence of xn's, and this is how they work. The first one is 2, and the n plus 1 you get for taking the nth one, adding 1, and then dividing by 2. And that's fine. I mean, I'm not telling you what the elements are, but I'm telling you how you can get them with this recursive formula, right? So for example, if I wanted to know what's the second one, well, I follow these instructions. The second one is x1 plus 1 divided by 2. So then I plug the 2 here, and that would be 2 plus 1 divided by 2, or 3/2. And then if I want the one after that, well, I just follow the recursive definition. Take this 3/2, put it here, add 1, divide by 2. So this is 5/2 divided by 2, that's 5/4. And so on, right? There are others that can be doubly recursive, you know, like the Fibonacci sequence. Can't resist putting it here. So Fn, where F1 and F2 are 1. And then you get Fn plus 2 by adding Fn plus 1 and Fn, or n greater than or equal 1, right? So in this case, the elements are 1 and 1 out of the first 2. And then to get the next one, you add the previous 2. So the next one is 2. And then the next one is the sum of the previous 2. So that will be 3. And then after that, 2 plus 3, that's 5. And then 3 plus 5, that's 8. And then 5 plus 8, that's 13, 21, 34. This actually grows exponentially. So the numbers start getting really, really big. Good. So that's going to be the end for today. We'll continue next week, and we'll talk about properties of sequences. And we're going to use sequences to talk about series later on, and then talk about limits, and all the other extra things that you know from calculus, derivatives, integrals, and so on and so forth. All right, so I'm going to stop right here.